Galaxy experts have come from all over the world to an intimate workshop held at the Lorentz Center, part of the Leiden Observatory. But even while they ponder today's favorite theoretical problems, data is being returned from some of the world's most advanced astronomical instruments, probing the sky not for optical light nor radio waves, but for heat. Infrared observation has finally allowed astronomers to see the stars hidden behind the dust that populates the galaxy, and it's only been possible from space. In the early 90s, Derby, the diffuse background experiment on NASA's Cosmic Explorer satellite, opened new windows on our galaxy at 10 wavelengths all across the infrared spectrum. At the shortest infrared wavelengths, corresponding to the hottest sources, the radiation comes mainly from stars. They clearly outline the central bulge of the disk, with lots of nearby bright stars filling the sky. But as we switch the camera to longer wavelengths, the picture changes dramatically. The bright thin disk along the galactic plane is still there, but the central bulge of hot stars has almost gone. However, right across the sky is a fuzzy S-shaped band of light called zodiacal light. It comes from very close by, interplanetary dust heated by the sun in our own solar system. At even longer wavelengths, this re-radiation from warm dust becomes even more prominent. But now we can see intense radiation from interstellar material concentrated along the galactic plane and extending well beyond the nuclear bulge. At the very longest wavelengths, we are looking at cold interstellar dust. Wispy traces seem to fill our view of the entire sky with no identifiable features. All very pretty, but what do these images tell us about the shape of the Milky Way? For instance, is there evidence for a bar-type feature in the center of our galaxy, as in this one? This might be an indication of how our Milky Way has evolved. In this picture, all the data have been combined to remove the effect of dust and show directly the distribution of the stars near the central bulge. The brightness has been color-coded from white through red down to green and blue for the faintest stars.
The question now is, can we see evidence in the shape of this light distribution for a bar-like feature in the Milky Way? When we look carefully now at this 1 micron map, we see that indeed it is a little bit fatter looking to the left of center than to the right, and it is indeed a bit brighter at each point to the left of center than the corresponding point to the right of the image. So the Derby data, giving us a multi-wavelength view of the central bulge of stars in the galaxy, is supporting the idea that the Milky Way might indeed be a barred spiral galaxy.
Radio observations also show evidence for the existence of a bar in the central parts of our galaxy. If the orbits of the gas were circular, then there would be a sharp transition as the line of sight crossed longitude 0 between positive velocities and negative velocities. In fact, the observations both of neutral hydrogen and of carbon monoxide show a blurring in this transition across longitude 0. This blurring is consistent with motions along elliptical orbits associated with a bar. Moving from the length scale of the bar, we find a region which is a unique laboratory, where phenomena occur which occur nowhere else in the galaxy, right down in the center.
In this impressive radio image of the central few hundred light-years, we can see dramatic evidence of streams of ionized gas moving rapidly along strong, arching magnetic fields. As we approach even closer, we see wispy filamentary shapes in the central few light-years, curving away from a bright radio source. And at the highest resolution, astronomers have identified Sagittarius A star as the compact source at the very center. To see if there are stars behind these whirling curtains of dust and plasma, astronomers must look in the infrared wavelengths.
Now, when I first saw this picture, I was really astounded by the great detail. You could see, obviously, single objects, single stars in there. And when looking at different colors, different wavelengths in the infrared, we can actually now see that these individual stars have individual colors, infrared temperatures. Now, what could Sagittarius A star, the radio points us, actually be? Now, the most plausible explanation probably is that it is, in fact, the very center and a very massive central black hole. To really find out whether or not there in fact is a black hole in the galactic center, we need to measure closer in.